Hello everyone, welcome back to Online Mathshop. Okay, I saw this interesting video about these expressions 0 divided by 0, 0 power 0, infinity power 0 and 1 to power infinity, and we want to actually find out the meaning. So I'm bringing this video to you guys so that you actually want to cheat and see how this guy explains the meaning of all of these systems, and then you also have a better understanding of what it is. So just go through the video, watch it, and let me have your thoughts in the comment section.
Today I'll talk about these crazy expressions here. Now in school they tell you that if you don't stay away from these, eternal damnation awaits. And that's actually a pretty good rule to pass on to the masses to prevent them from suiciding. But if you actually stop there, a lot of modern mathematics is not possible. So let me explain this a little bit. Alright, so why do they tell you that you can't divide 3 by 0, or that 0 divided by 0 is undefined? Well, let's have a look at something that nobody has a problem with, 3 divided by 8. So in maths, 3 divided by 8 actually just stands for the one and only solution of this simple equation there. 8 times x is equal to 3. Okay, so let's change 8 to 0 and see what happens. Well, we're immediately in trouble here because no number satisfies this equation. The equation will always be 0 is equal to 3. It's always wrong. So it sort of makes sense to stay away from something like this, right? And so what about 0 divided by 0? Well, a different problem comes up. Here, every single number actually satisfies this equation. So there's also trouble. Let's just stay away from it. So for most people, that's all they really need to know. But now, if we had stopped there in mathematics, there would actually be no calculus. And nobody would know Isaac Newton. That would be really sad, right? Okay, so what's calculus about? Calculus is all about derivatives and integrals. So here I've drawn a nice function, and we want to find the derivative of this function at a certain value. Now you all know that this stuff is incredibly important, but it has a really simple geometrical interpretation. Interpretation is the derivative here is just the slope of this touching line. Now, just reading off from the function, it's not clear what that slope should be. Now what's easy to calculate is actually the slope of a cutting line like this. And then, the idea is if I move these 2 points of intersection together, then the more they come together, the closer the cutting line will be to the tangent line. And the closer the slopes of the cutting lines will be to the slope that I'm really interested in. Okay, and now how do I actually calculate the slope of the cutting lines? Well, you can just immediately read off what the height here is and what the width is, and then we get the slope, just height divided by width. Pretty obvious. But now, see what happens when I move the 2 points together. Both the height and the width approach 0. So overall, the slope approaches this forbidden 0 divided by 0. But now, nothing really terrible happens, right? You would expect something terrible happens, but nothing terrible happens. We're just getting closer and closer to this slope of the touching line. So that seems a bit strange. But just remember, that equation that corresponds to 0 divided by 0 has all numbers as solutions. So what really happens here is that we've established a context, a very narrow context, in which 0 divided by 0 kind of makes sense as one particular number. And you can see as the context changes, we get different numbers out here. So let's just have a look at a specific example. Let's just calculate the derivative of x squared at half. Right, so we have to see what's the width here and what's the height. Width, we call it w, so that gives us a second value. Now we evaluate the function at these two values, so it gives us half squared and 1/2 plus w squared. Now height is of course the difference between the two, so that one here. Expand the top, notice that these two things cancel out, and you've got the height. And with the height, we've got the slope. And you can see the slope really, what does it do? At the top it goes to 0, at the bottom it goes to 0, but as long as it's staying off 0, we can actually cancel the w. And what this gives us is this nice expression here, and just by looking at that it's completely obvious what the limit of this expression is as w approaches 0. That's the slope we're after, and that means that the derivative of x squared at 1/2 is equal to 1. Isn't this neat? Now, half was actually not very special here. We could have used any initial value here, and if we did that, we would find that the derivative of x squared is 2x. So once we've got that, we've got this whole thing under control as far as calculus is concerned. All right, so we write this like that in calculus books, and actually if you have a really, really close look, you also find that the 2 was nothing special, so we could have done the same thing for 3, and you should really try this, or for 4, or for 5, or just in general for any positive integer, not a big deal. And now we just run with the scheme and make up a huge table of derivatives for all sorts of functions that we're interested in. And so you have it. In a nutshell, calculus, courtesy of 0 divided by 0. Pretty neat, isn't it? So really that apple that hit Newton there at some point in time and made him invent calculus was definitely a 0 by 0 apple, right? Before we go on, and if maybe you don't believe anything I said so far, let's just ask our smartphone what 0 divided by 0 is. So, Siri?
Imagine that you have 0 cookies and you split them evenly among 0 friends. How many cookies does each person get? See, it doesn't make sense. And Cookie Monster is sad that there are no cookies. And you are sad that you have no friends.
That's fun. But now I also promised you all of these guys. It is very important to make sense of these, and actually it's done in calculus book in the chapter on indeterminate forms. And if you have a look there, you find that these slope quotients that we had a look at so far actually are just a special incarnation of this sort of setup. So you have a quotient of two functions, g and h, and a dependent variable, in this case t. And as the variable approaches a critical value, both g and h approach 0. Whenever you get something like this happening, then you say that the quotient takes on the indeterminate form 0 divided by 0 at the critical value. And actually, just here, I better say, the critical value can also be infinity. Okay? So t can also go off to infinity. What makes this whole thing indeterminate? Well, by just looking at the information we've got so far, it's not clear at all what the quotient does as we approach the critical value. It could go to a specific value, it could go to infinity, or it could do nothing reasonable. On the other hand, if you were to consider the product, you don't have to know anything about g and h except that they both go to 0 to conclude that the product will go to 0. And even Siri knows about indeterminate. So if you ask about any of those strange expressions that I showed you, Siri will tell you they're all indeterminate. So let's just have a look at an example, 1 to the power of infinity. So infinity, I just really have to say this, in elementary calculus, never stands for anything like a number. It always stands for some sort of function or process that goes to infinity. The same sort of thing here, both 1 and infinity actually stand for functions. The first one approaches 1, the second one approaches infinity as t goes to a critical value. And this is also indeterminate, meaning that if you don't know exactly what you're talking about, which g and which h you're talking about, the g to the power of h could approach any sort of finite value, or it could go to infinity, or it could go anywhere you want. Okay, so here's a really famous example of something like this. 1 plus 1 over t to the power of t. So here the critical value is actually infinity, so t gets bigger and bigger. And as t gets bigger and bigger, this 1 over t will approach 0. And so the whole orange bit will approach 1. And of course, the exponent will approach infinity. And it's really, really important to say that you can't do first the one limit and then the other one. It's really the speed at which one expression goes to 1 and the other expression goes to infinity that determines the behavior of the whole expression. Okay, in this case, it approaches this value here, very famous. It's the base of the natural logarithms, it's e. And there's a whole video that I've done about this indeterminate form. Maybe watch it again after you're finished with this video. So you have a look at this and you think that, well, to make sense of all of these strange expressions, you have to invent a lot of different sorts of mathematics. But it actually turns out that all of these expressions, and that comes really as a surprise to many, many people, are just 0 divided by 0 in disguise. So all of these expressions can be reduced to just a consideration of 0 divided by 0. And I just want to show you how that works for 1 to the power of infinity. So again, that just corresponds to this. Now, this whole thing is equal to e to the power of log, that whole expression. And now we're dealing with a logarithm, so we can pull the exponent in front of the logarithm like that. G goes to 1, Now log of 1 is 0, means that this whole thing here goes to 0. Now h goes to infinity, but we can also write the whole exponent here in this form, and then the 1 over h actually goes to 0. So what we've done now is basically reduce 1 to the power of infinity to a 0 divided by 0. Pretty neat, right? And you can do this for all the other ones. So far, apart from this very, very simple x squared example, we haven't actually figured out any other expression. So how do you actually do this in practice? What I've tried to push here is that the apple that hits Newton was really a 0 by 0 apple, a 0 by 0 apple makes calculus, but you can also go the other way around. Once you've got calculus, you can actually hit the 0 divided by 0 with it. But how does that work? Well, that's a bit of magic, and it's called L'Hopital's rule. So here is an indeterminate form 0 divided by 0 at 1. So if we let this thing go to 1, both the top and the bottom go to 0. And now how would you actually figure out where the whole expression goes to? We could try and evaluate this at t's that are very close to 1. That's a perfectly fine strategy, but there's actually a really nice shortcut. So what you do is you take the top and find the derivative, and you take the bottom and find the derivative. So the derivative of the top is 1 over t, and the derivative of the bottom is just 1. And now you see what happens to this expression as t approaches the critical value. And of course, nothing terrible happens here at all. This just becomes 1, right? And now, if the function that we're dealing with here are nice, differentiable, check out the details in the calculus book, then we can actually conclude at this stage that what we're really interested in also goes to 1. Really, really nice trick. So overall, what we've seen is that to make sense of 0 divided by 0 in calculus just means sort of setting a special kind of context and sneaking up on the zeros. So the same sort of thing if you want to make sense of 3 divided by 0. You also do this by sneaking up on 0. And of course you know that things explode magnitude-wise, and you can make sense of this in this way. But that's not the end of it at all. So in higher levels of calculus, it actually makes sense to treat infinity like a number and to actually write equations like 3 divided by 0 is equal to infinity, and you really mean it. So these things don't stand for any kind of functions, they really stand for, 3 as a number divided by 0 as a number is equal to infinity, sort of as a number. In other branches of mathematics, you sometimes find that it actually does make sense to set 0 divided by 0 equal to 1. That's just topic for another video, so let's just leave it at that.